Hello everyone, I'm Professor Harrison, and welcome back to our module on regression analysis. Today we're going to be covering Newey-West standard errors, which are the standard fix for the autocorrelation issue that we ran into last time. We're following Margot, a graduate student trying to reassemble a story that her family buried. She's right back at the same regression, the one where her grandfather's returns showed errors that were correlated over time, and she needs to repair the standard errors before she can trust a single test that she runs on it. She pulls up another page from her grandfather's fund records. Let's pick up exactly where we left off. Margot is regressing her grandfather's monthly fund returns onto the market, trying to figure out whether there was any real return beyond that of what the market handed him, if he had any genuine skill. Last time we found a real problem. The errors in that regression were positively autocorrelated. The coefficients were fine, but the standard errors were too small, which meant the t-statistic on the intercept was unreliable. We couldn't trust the inference, and today we're going to fix it. The fix is a different way of computing the standard errors, called Newey-West standard errors. You'll also see them called HAC standard errors, which stands for Heteroskedasticity and Autocorrelation consistent. That name tells you exactly what they're built to survive. Now we've actually seen half of this idea already. Back when we covered heteroskedasticity, we used white robust standard errors. Those fix the case where the error variance changed from observation to observation by building the standard error out of the actual squared residuals instead of assuming one constant variance. Newey-West takes the same idea and extends it. On top of letting the variance change, it also lets the errors be correlated with each other across time. So instead of just using the squared residual, it also adds in the products of residuals at different lags. Those are the pieces that capture how this period's error relates to the earlier period's errors. Correlations between nearby periods get more weight, and correlations further apart get tapered down toward zero. So how exactly do Newey-West standard errors work? Let's see why those cross-product terms are the right thing to add. Think about what the product of one residual with the one before it actually tells you. When errors are persistent, a positive residual tends to sit next to another positive one, and a negative will sit next to another negative. So you're multiplying two numbers with the same sign and the product comes out positive. When errors alternate, you're usually multiplying a positive by a negative, so the product comes out negative. And when there's no relationship at all, the signs are unrelated, and the positives and negatives are going to roughly cancel, and the products average out to about zero. So the average of those products is a direct readout of autocorrelation. Positive when the errors persist, negative when they alternate, and near zero when they're independent. That average is exactly the quantity that the ordinary standard error quietly assumes is zero. Newey-West stops assuming it, and it measures it from the residuals and adds it back in. It also doesn't just assume autocorrelation of just one lag. It's possible to be autocorrelated across multiple lags. In fact, Newey-West puts more weight on the closer lags and tapers down towards zero for the farther away ones. That tapering raises a practical question though. How many lags should you go back? This is the one choice Newey-West asks you to make, and it's called lag-truncation. Go too short and you miss real dependence. Go too long and the estimate gets noisy. The common rule of thumb is to set the number of lags to roughly the sample size raised to the 1/4 power. A slightly more refined version is 4 times the quantity sample size over 100 raised to the 2/9 power. For Margot, 20 years of monthly data is about 240 observations, and both rules put the number of lags at around 4 or 5. So she recomputes the standard error on the intercept the Newey-West way, allowing for the autocorrelation she found. And the standard error gets noticeably bigger. The t-statistic that looked comfortably significant under the old formula drops below the threshold. Once the errors are accounted for honestly, the apparent skill in her grandfather's track record is no longer statistically distinguishable from zero. It was never really there. It was an artifact of standard errors that were too small. This is exactly why Newey-West became the default in empirical finance. If you open almost any asset pricing paper, the standard errors are going to be Newey-West whenever you're dealing with time series data. Financial time series tend to have both problems at the same time. Volatility clusters, so the variance shifts, and returns and errors persist, so they're autocorrelated. HAC standard errors handle both at once without making you commit to a specific model of either one. There are other routes that you could take. Generalized least squares transforms the data to strip out the correlation before estimating, or you could model the error process directly and estimate it. But both of those ask you to specify the structure of the dependence, and if you specify it wrong, you can end up much worse off than when you started. Newey-West doesn't ask you to know the structure, it just says stay robust to it. So that's why it ends up being the default in empirical finance. Margot puts down the fund records for the last time. She realizes that her grandfather's skill had never really existed, and everything that he built his life on had actually been stolen from Ruth. Margot kept coming back to the numbers at the end of those last letters. She already knew that they weren't random. She'd found them, she'd seen the dependence in them, and each value carried a trace of the ones before it, the same signature she'd been taught to spot in a regression's errors. What she hadn't known was what to do with it. Today's lesson answered that, and when a sequence hides dependence underneath, you don't throw the dependence away. You model it and the truth comes out. So she treated the numbers as one long sequence and measured that dependence exactly lag by lag. Each one turned out to be a fixed weighted combination of the numbers before it. The pattern was perfect and clearly deliberate. Recognizing those weights from the autocorrelation as a linear system, the autocorrelation matrix times the vector of weights equals the vector of autocorrelations. She'd seen that kind of system before. It was the matrix algebra at the center of Ruth's dissertation, the work Victor took and never understood well enough to use. Margot solved the system. It gave her back a stream of numbers, but she wasn't quite sure what they meant. Turning back to her letters, she noticed that next to each code was the words, "I leave it all to the next rational quant." Realizing what they mean, she runs quickly to her local bank. She discovers that the numbers were a bank account number and that her entire family fortune had been saved there the whole time. Ruth hadn't stolen it all back for herself, but she had moved it out of the hands of Victor long before the end. Also, the fortune could end up in the right place, in the hands of the next rational quant. Margot finished her thesis that spring. On the first page, before anything else, she credited Ruth Sokolova by name. Upon graduation, Margot looks forward to the future, ready to carry on Ruth's legacy. So that's Newey-West standard errors, and that's the last tool we're going to add. When your errors are heteroskedastic, autocorrelated, or both, your coefficients will still hold, but your standard errors won't. And HAC standard errors repair the inference without forcing you to commit to a model of the problem. You pick a lag length, you let the data's own variance and correlation structure do the work, and you end up with standard errors that you can actually trust. It pulls together the last two videos into one robust calculation that stays valid under both problems at once. And with that, our toolkit's complete.